Right, very good morning. I welcome aboard again to Tone Academy on the T1 channel. Yes, today we'll be discussing Pauli's exclusion principle, well, in detail, right? Now, why Pauli's exclusion principle? First of all, what is the aim of Pauli's exclusion principle? Let me write the aim first. But before that, I would like to quote something for you. We have, so many people with great identities. Please understand that. You might be having billions of people on the earth, or even billions of animals, or all the things on earth. But let me tell you that each one has its own identity. Take the case of humans, right? Each one have their own DNA. Each one have their own name, right? Each one have their own identity. Similarly, when I say an atom has infinite number of orbits, you can actually place infinite number of electrons in all the atoms. You must understand that. Now, similar to what we have identity, similarly, even every electron has identity. If in a classroom, if someone is called by their name, right, they say, hi, hello, right? Similarly, the electrons, which are, can be in infinite in number, because you have infinite number of shells within the atom. Every electron has its identity, right? And as we have names, as we have specific DNA, right? Similarly, electrons will be having their own identity, and electrons will be having their own DNA. You can actually say that. That is the basic, aim of Pauli's exclusion principle. Now, the only thing which is different from you, me, and the electron is basically, we have our different names, right? But these names are not the way to give identity to the electron. We have a separate technical terms where we can actually give identity to the electrons. That's what is our discussion. That's what is Pauli's exclusion principle. By this time, you must be understanding the gist of it. Why Pauli's exclusion principle? Well, I can say that an atom has infinite number of shells, infinite number of orbits, infinite number of non-radiating parts. All the three are synonymous. So once you have infinite number of shells, you can actually place infinite number of electrons. Now the issue arises, if you have infinite number of electrons, do we have an identity similar to what we have outside? And the answer is what? Of course, yes. We do have identity can be placed for each and every electron, and believe me, and if you say hello to an electron, it can say hello to you also, right? So if someone is asking you what is Pauli's exclusion principle, then I would like to say, I'm writing the aim first of all. Look at this aim. The aim is to provide, I want everyone's attention. The aim is to provide. The aim is to provide, not just reading the statement given by Pauli. Let us draw inferences. What is there in his heart? What is that he wanted to tell? Then you will understand the total concept. So I draw the attention. I'm writing the aim, not the statement given by Pauli yet. I'm writing the aim. To provide, right? Identity. To provide identity. As we have our own identity, similarly electrons will be having identity. Do these identities exhaust? No, absolutely not. You give me infinite number of electrons also, that electron's identity can be easily placed. That's what Pauli is telling us. Now, if someone is asking you, someone is mugging the statement of Pauli, you just tell him, why are you mugging this? What is the aim of it? Then the aim is to provide identity. I would like to underline. To provide identity to each and every electron. To each and every electron. Well, you must understand, to provide identity to each and every electron in an atom. You must understand this. So if someone is mugging, your brother or sister or your friend is mugging the statement of Pauli's exclusion principle, you should pause her or him and tell him what is the purpose of the Pauli's exclusion principle. Then you need to tell him that yes, as we have identities outside, right? When someone is calling by our name, we say hello, hi. Similarly, we can actually place names or provide identity to each and every electrons in an atom. Now, people will ask you, do you have so many names? The answer is, of course, yes. You give me n number of electrons, I can provide n number of what? Identities to each and every what? Electrons. Now, what is the identity which we are speaking of? What is the identity? Do we have the same names as Shekhar, Suresh, or Naresh or something like that? No, absolutely not. We don't have such names for electrons. But outside, as we claim that you are Chandrasekhar, then you say hi. Similarly, an electron will be having its own name. And you wanted to know the name because the name is itself is the identity. That's what I'm speaking of. Right? So what can be the electron names? Well, you wanted to know that? Yes, I draw the attention of everyone. Look into this. This is basically the name of an electron. In fact, the identity, I draw the attention please. The identity of the electron, or I can simply say it is the name of electrons, mind you. That is the name which I am providing it for the electron. The identity of an electron, right? And the identity, the name of the electron will be like this. Well, observe, look at the name of the electron. Look at the name of the electron I am writing. And you call by this name, the electron will say hi to you. I am not joking. You must understand that, right? So remember, the identity of an electron is through, it is like this, N, L, M, and S. Look at this identity. The identity of the electron is basically N, L, M, and S. Now, what are all this? Remember, these are nothing but quantum. It is basically quantum number set. You must understand. So, the combination of principal quantum number, that is the shell, the combination of L, which is azimuthal quantum number, that is nothing but the subshell, and the M, which is magnetic quantum number, which is further divided as orbital, and then the S, which is having a clockwise spin or an anti-clockwise spin, that is actually basically told. And remember that not a single quantum number is giving identity to the electron, mind you that. So it is a combination of all the four quantum numbers set together is nothing but the name of the electron. Right? And remember and recollect, when we were discussing atomic structure, we were basically telling that N is nothing but the principal quantum number, that is a shell. This is the subshell, L is subshell, M is orbital. And I was warning students, I warned students, earlier also I have done that. You cannot be casual in substituting orbit and orbital, you must understand. Both are different things. Orbit is something which is in a larger area, larger volume, you must understand that, right? As I told you. And orbital is a smaller space. But mind you, this, N, L, and M are all spaces. And they all represent spaces where the electron spends most of its time. And S is nothing but the spin quantum number, which is actually telling the spin of an electron. Because the electron will be revolving, it's spinning on its own axis like this, and then revolving around the nucleus. You must understand. So that spin is actually the clockwise spin or the anti-clockwise spin is given as a spin quantum number. You must understand that. So the critical part of my discussion is this only. What is that? It's basically if someone is asking you, what is Pauli's exclusion principle about? Then it's basically providing identity to each and every electron in an atom, and the identity of the electron is in the form of what? Quantum number set. You must understand. So if you ask me in one word, what is Pauli's exclusion principle? What are you doing? Well, I can simply say it is nothing but naming ceremony. It's basically naming ceremony. As we have naming ceremonies, we have functions. When someone is born, we wanted to name them. We wanted to provide identity to them through their surname, whatever. Similarly, electrons naming is naming ceremony itself is what? Pauli's exclusion principle. And let me tell you, it's not limited. It's not limited. Well, you give me infinite number of what? Shells, you have infinite number of electrons. Similarly, I can provide you names for any number of electrons. You don't get worried about it. You give n number of electrons, I can name the n number of electrons and they are given identity. right? So basically, if you wanted to explain to your sister or brother back home in school, and she or he is mugging the Pauli's exclusion principle, and you wanted to know what exactly is it, it's nothing but what naming ceremony. You must understand that. Do we have the similar names as we have outside? No, absolutely not. We have NLMS set, which is nothing but, I can simply say for your understanding, this is nothing but the name of electron. You must understand, that's the name of electron. Right? Now what we will do, we will actually quote the Pauli's exclusion principle, why it is called exclusion, and then we will take up an example, and then we will try to name the electron, and the naming of electron itself is a question in the exam, you must understand. It itself is a question in exam, right? So let us go ahead and write with the due respect of the to Pauli with inverted commas. Let me make a statement, right? Shall I? Watch carefully now. So before I rub it off, here is the case. To provide identity to each and every electron in an atom. Identity is nothing but the name of an electron. The name of the electron is a combination of NLMS, that's nothing but quantum number set. And now we will write what exactly is Pauli telling us about the providing identities. So simply we are doing today naming ceremony, not for you and me, it's for electron, right? Let us see. Observe carefully. Now what does he say? What does he say? Why is it called exclusion principle? Well, I would like to say, in inverted commas, I can simply say, no two electrons can have same set of quantum numbers. Look into this, what he is telling. No two electrons can have same set of quantum numbers. Quantum numbers, set of quantum numbers, that's a combination of NLMS, right? So if you take n number of electrons, infinite number of electrons, and if you try to name an electron, no two names are similar. Now it's a common sense, when no two names are similar, no two DNAs are similar, then you have your own identity. That's what I'm telling from the beginning. If someone is claiming two electrons don't have the same quantum number sets, don't have the same DNA, don't have the same identity, then I think you are actually fixing that electron, and you are giving an identity to the electron. That's what is there in the heart of Pauli. You must understand that is inference, right? So if he says that no two electrons can have the same set of quantum numbers, that means that, you know, when they don't have the same set of quantum numbers, you are indirectly telling the electron, you're basically telling the electron that I'm giving you an identity. And when I call by your identity, you should say hello to me. You must understand, because in infinite number of electrons, I am in a position to actually give infinite number of identities, then naturally you must understand that you are providing identity. That's why I call the Pauli's exclusion principle to be a naming ceremony. You must understand that, right? If that is the case, now what will happen? Now if I can write, if the sets are same, if I say, if the set of quantum numbers are same, if the set of quantum numbers are same, or otherwise I can write a question rather. Well, now if I can see, why is it basically called, I'll draw the attention of everyone, please. I draw the attention. Now I am explaining each and every word in that, right? Why is it called exclusion principle? Why are people using this word? Why is it called exclusion principle? Why is it called an exclusion principle? Well, I would like to explain this, right? When someone is claiming two electrons cannot have the same set of quantum numbers, and then why is it called an exclusion principle? Well, my answer to this is, suppose, right, if two electrons, watch carefully here, if two electrons have same set of quantum numbers, well, if you assume and go against the Pauli's exclusion principle, he says that no two electrons can have the same set of quantum numbers. No two electrons can have the same set of quantum numbers. And here you are claiming that suppose if two electrons have the same set of quantum numbers, then what will happen is the issue. You're not supposed to have the same set of quantum numbers. And suppose if the electrons are having the same set of quantum numbers, then look into this, what he is telling us. Right? Then, I'm underlining this. Then, such electrons are excluded. Look into this. If two electrons can have the same set of quantum numbers going against the Pauli's exclusion principle, then what he's telling us is basically, if two electrons have the same set of quantum numbers, then such electrons are excluded from entering into the constitution of the atom. Let me tell you this. Entering into the constitution of the atom. That means that in a simple language, I can simply say, if any two electrons are having the same set of quantum numbers, you're basically kicked out of such electrons are kicked out of the atom, and they have no place in the atom. And he is telling in his own words, he's basically telling that such electrons are excluded from entering into the constitution of the atom, and hence, it is called exclusion principle. It is called exclusion principle. If two electrons are having same identities, if two electrons are having the same quantum number sets, then such electrons are excluded from entering into the constitution of the atom. Such electrons are kicked out of the atom. Remember, they have no place in the atom. And since he is telling they are excluded from entering into the constitution of the atom, and hence it is called exclusion principle. You must understand this. Right? So remember, that's what is the aim. Now let me give an example. Let us take a straight examples, right? Straight example, and check out, right, how, and this principle in practice, how do we actually name these electrons? We have found out that it is nothing but naming ceremony. So let us start off naming the electrons in a proper way. And I'm basically reminding you, if I'm giving you 100 electrons in your atom and ask them to place inside the atom, you're not throwing away. You are not throwing away randomly. You have a regular arrangement. When I say you have a regular arrangement, you have a scheme of what? Distribution of electrons. You have a scheme. You have to first distribute in the lower energy levels, then higher energy levels, then higher energy levels, right? And each shell can have a capacity of maximum electrons, right? Why all these conditions are set up? Let us actually discuss in Pauli's exclusion principle. We'll put this in practice, right? Now we are actually getting into the naming ceremony. Now what I will do, I will take few electrons from the shells and try to name it, and believe me, very seriously, I'm joking. If you can maintain absolute silence, and once you name the electron, and when you say hi to the electron, it will actually reciprocate to you saying hi, right? Remember this, and remember, let's actually go and put in the names for the electrons or identity to the electrons, and answer a few questions. Why there are certain questions? Why, what are the questions also? Let's discuss this. Now, when we wanted to name the electrons, you and me must be picking the electrons only from the shells. Because where are the electrons in an atom? Well, the electrons are there inside the atom within the shells, within the cells. So what I will do is take up the electrons from the shells itself. When you wanted to take the electrons from the shells, let us start off with the first shell. Let us start off with the first shell and check if any subshells are there, and if a number of electrons that they can accommodate, and then go from there, because that is how the sequence is, right? So I'm picking out. Basically, I'm picking out electrons from the shells. And if I wanted to pick the electrons from the shell, well, I would like to start off from the first shell. Let us see here. And first of all, please recollect, name of electron is basically L, M, and S. The combination of 4 is nothing but the name of electron, right? And suppose if I take n value 1. Let us start off from the first shell, because you need to name the electrons in the shells, because electrons reside only in the shells. Right? So if I put n is equal to 1, that is the first subshell. Well, if I say 1, then you know n value is equal to 1, that is the first shell, and then L values will be 0 to n minus 1. So it will be 0 to, if I substitute 0 to 0, that is nothing but 0. So please understand that if n is equal to 1, L value is equal to 0, and M value will also be 0, because M values will vary from minus L to plus L including 0. This I was actually discussing it to you. So if N value is 1, L value is 0, M value will be minus 0 to plus 0 including 0. That's nothing but the value. Well, in quantum physics, in quantum number physics, please understand it is not the value which is important. It is the number of values which is important. Right? So if I say for a given value of n, so I gave a value of n, there will be how many values for L? That's important. L is 0 is not important. Similarly, for a given value of L, how many values you are getting for M is also important. That's all, not the value itself, right? So M is 0, and spin can be, it can be plus half or minus half. That's what is the thing for n is equal to 1. So for n is equal to 1, you have L values, number of values to be 1, that is 0, and M values also to be 1, that is 0, and the spin can be plus half and minus half. Don't get confused. Please understand that it's not the value which is important. In quantum numbers, it is not the value which is important. It's not the value which is important. It is the number of values which you are getting. So my language, look into the language what I'm using. My language is basically, if n value is 1, the number of values for L is again 1, but that value is 0. That has no meaning at all. Remember that number of values is important for quantum number physics. You must understand that, right? So similarly, if L value is 0, the number of values for M is 0, is 1, that is 0. You must understand. Spin can be plus half and minus half. Now remember, if I say n value is equal to 1, that is 1. If L value is 0, it must be S. Because if L value is 0, it is S. If it is 1, it is P. If it is 2, it is D. If it is 3, it is F. This is what we were told in our earlier classes. Right? So if this is the case, here it is L0. So n is equal to 1. This is the principal quantum number if L0 is S. Right? And our teachers told us S can accommodate maximum 2 electrons. S can accommodate maximum 2 electrons. When our teacher was telling this, we would have asked our teacher that S can accommodate, why only 2, why not 3, why not 4, why not 5, why not 6, why not infinite? But our teacher was telling us, yes, S can accommodate only 2. Only 2. That's all. It's a rule. If that is the case, then we would like to explain that why S can accommodate only 2 electrons, and that's because of the restrictions put by what? Pauli's exclusion principle. So it's a critical, and I want the attention of everyone. Right, understand that one S can accommodate basically 2 electrons. S can accommodate only 2 electrons. We'll answer that, why only 2? But I think let us understand S can accommodate only what? 2 electrons. Now if the 2 electrons, now what we will do, we will give names to it. So we have started the naming ceremony. So we are providing names to the 2 electrons, right? And when I provide, let's take one by one. Let's take 1 electron and then do it. Remember, S can accommodate 2 electrons. This is the first electron. This is the other electron. Total are 2 electrons. Let me provide identity to this. Well, the identity of an electron is not your name, my name, Naresh, Suresh, Chandrasekhar, etc. But we have a separate name for it, that is NLMS. So why don't we put it? Well, remember that this electron is present in the first shell. So n value is 1. Right? N value is 1. And then we need to put L value. If n value is 1, L value is 0. Right? If L value is 0, then M value is 0. Right? Now what we will do, either you will move clockwise or anti-clockwise. You can't do both at the same time. Right? So you can choose one value from here. One value from here. So it is plus half. You can see here, this is plus half, right? Now I'm asking you, be silent, absolute silence, and say 100 half. You can call 100 half and it will say hello to you. I think you might be calling by this time now. Keep absolute silence and call the electron by its name. As you are calling me, Chandrasekhar or Naresh and Suresh, people say hi. Similarly, I am giving you time to call this electron and it will say hello to you. It will say hello to you. Mind you. So, okay, are you calling it? Yes, please call. 100 plus half. Yeah, you might have told half hi to you because that is how the name of an electron is. That is how the name of the electron is. Now you have the other electron. We have to name this. If I can name this, then I think you can have 1, 0, 0, and this time it's anti-clockwise, right? So you take one value at the time, minus half. Now watch this, watch this. If you call 100 minus half, it will say hello. If you call 100 plus half, it will say hello. And I'm sure you please call, you first name the electron, call the electron, maintain silence, and believe me, it will say hello to you. You must understand. So I'm joking, but please understand that I'm absolutely joking. It won't say hello to you. But remember, I wanted to induce into you that yes, these are the identities. Now question arises when our teacher was telling you can accommodate only 2 electrons. Someone wanted to say, I want to accommodate third one. Right? You wanted to accommodate third electron, then you put 1s3. I have no issues. I have no issues. It is 1s3. But our teacher was telling it S can accommodate only 2 electrons and the names are already written. The names are already written. But some fellow wanted to accommodate one more. If you want to accommodate one more, I think the third electron, if you see, this is the third electron name. This is the third electron name which I am writing. It also belongs to the first shell. It also belongs to the first shell, right? And if n value is 1, L value will be 0. And if L value is 0, again M value will be 0. Either you can have plus half or minus half. Suppose if you took plus half, then mind you, watch you, according to Pauli's exclusion principle, no 2 electrons can have the same set of quantum numbers. No 2 electrons can have the same set of quantum numbers. It's not permitted. So if you look into this name, this name, this name, and this name, they are same. This and this are similar. And no, sir, I don't want it to write this and I wanted to write other. Then if you write minus half, again this and this are same. So the third electron name is something which is similar to the first 2. And what Pauli is telling is, if the quantum number sets are same, such electrons are kicked out from entering and prevented or excluded from entering into the constitution of the atom, says Pauli. You must understand that. Right? So remember the exclusion principle. You can put one more electron, but I think that electron identity is either mapping with the first electron or the second electron, and such electrons are excluded from entering into the constitution of the atom, says Pauli. So that is the reason why your teacher was telling, you then S can basically accommodate only 2 electrons and not 3. And why? That's because your teacher was insisting on 2 electrons. It's not the case. It's because of the Pauli's exclusion principle. Someone is asking, why S can accommodate only 2 electrons? Then you must answer him. If you put the third one, right, then you must understand that electron will be having the same set of what? Quantum numbers. Similarly, you can go for n is equal to 2. Similarly, if you can go for n is equal to 3, you will get number of electrons, right. You have n number of electrons. And then you know, if the identities are different from the other, you will stay inside the atom. If you actually go for more than that, then I think you would be kicked out of the atom. Similarly, our teacher was telling it's case of SPDF. Your teacher was telling this can accommodate maximum 2. If someone is asking why, if you wanted to put third, that identity is similar to the first 2. Hence you are kicked out. Similarly, your teacher told P can accommodate only 6. If someone is insisting, I'll put 7, what will happen? If you put 7, then the name of the 7th electron will be similar to any of these 6 electrons, you must understand. And such electrons are kicked out of the atom and prevented from entering into the constitution of the atom, says what? A Pauli, and hence the exclusion principle. Similarly, your teacher told this can accommodate 10. So if someone is asking, I'll put 11. What will happen? If you put 11, then understand that the 11th electron will be having the same quantum number set as D. So that is not possible. So if F can accommodate only 14, if someone is telling I'll put 15th, what will happen? Then the 15th electron name will be similar to these 14s, and that's why we have restrictions, we have limitations. That's what our teachers was telling. S can accommodate 6, P can accommodate 6, D can accommodate 10, and F can accommodate 14. That's because of the Pauli's exclusion principle, where no 2 electrons are supposed to have the same number of quantum sets, and hence the exclusion principle. I think what you do, you practice it for P is equal to 6, D is equal to 10, and F is equal to 14. You get 6 sets here, you get 10 sets here, you get 14 sets here, you get 2 sets here. Once you practice it, you will find that, in all these sets, no 2 sets are similar, and hence the exclusion principle, right? Well, after Pauli's exclusion principle, I think you followed it. And remember that you practice at home how actually P can accommodate 6, D can accommodate 10, and F can accommodate 14, not more than that. So you have restrictions placed within the shells, how many electrons can revolve in a particular orbit. So it's basically, see, what is surprising to me, what is basically surprising to me is, there is scheme of distribution of electrons within the atom. You must understand, very strange, very strange. There is absolutely no randomness at all. In fact, randomness is 0. Disorderness is 0 within the atom. You must understand. So when you have a scheme of distribution of electrons, natural thing which adds to that is basically we are providing identity. I am a proud person today. I am so proud. We should be proud. Not only me, you should be proud by this time. By this time, right? You must be proud by this time. Understand that we are actually providing what? Identities to electrons, and I'm very proud because infinite number of electrons, and you are able to put names, and now that is the case of what Pauli's exclusion principle. So basically it's nothing but naming ceremony and without any restrictions. Now naming ceremony can be okay, fine, but you have infinite number of electrons and have placed names for all the infinite number of electrons is really great, right? You must be proud of it once you have done this, what I told you. Right? So if that is the case, I go for the next principle or rule. Watch carefully here, and the combination of this and the Pauli's exclusion principle and the Aufbau principle will be a question in the exam. So what I will do, right, there is a rule. As I told you, the scheme of distribution of electrons are not done by someone's dream. The scheme of distribution of electrons is not done by someone's dream. They are guiding principles and guiding rules. And one of the principles I told you earlier is Pauli's exclusion principle. And the second one today I told you is the naming ceremony, that is the Pauli's exclusion principle. And then now I draw the attention of everyone. And here comes the other rule, that is the Hund's rule of maximum multiplicity. The Hund's rule of maximum multiplicity. You should understand this. Right? Hund's rule of maximum multiplicity. Now, what exactly is this? What exactly is Hund's rule of maximum multiplicity, and why this rule? First of all, understand a few points that, atom or electrons, what they do, they are dynamic, right? And once you are born as an atom, right, it tries to attain stability. Now, we were told that atoms combine, giving you what? Molecules. So when atoms combine, giving you molecules, why do they do that? Why do they do that? Because to attain stability, you must understand. Now, what is stability? Stability is having the lowest energy state. The lower the energy in you, the more stable you are. The more the energy in you, I think you are unstable. You must understand. This is the fundamental. So, stability is basically a function of what? Energy. Something of that type is linked to this Hund's rule of maximum multiplicity. And as I told you, it's not random placement of electrons. You have a scheme of distribution of electrons which we should follow. Right? Now, what is Hund's rule of maximum multiplicity? And let me tell you that the combination of Aufbau, the combination of Pauli, the combination of what? Hund's rule of maximum multiplicity, all the three together will be asked in the exam. So everyone must understand that this assumes significance. Before I go there, let's see what is Hund's rule of maximum multiplicity. I'll put it in a simple way. Watch carefully here. Now, I actually write its statement before I actually write my own understanding, and I'll induce into you the similar thing. Now, what he wanted to say, he says that this all things is this. While writing electronic configurations, remember, while writing electronic configurations. Now, if anyone is attempting to write the electronic configuration, he will be using Aufbau's principle. So, it's nothing but configuration is nothing but the scheme of distribution of electrons within the shell. There are some rules which need to be followed. If I give you 10 electrons, you're not throwing away electrons in any corner which you like. You're not doing that. We are to follow the Aufbau principle, first fill lower, then fill higher, then higher. So that I gave you a scheme of doing that in the Aufbau principle. You can actually check it out, that class, right? So while writing the electronic configurations, you know what he's telling is, electrons enter. I draw the attention. While writing the electronic configurations, electrons enter. I write a technical word, don't get threatened. Watch. Electrons enter, degenerate orbitals. Don't get threatened. I would like to explain this. Right? But let me finish off the statement first. While writing electronic configurations, electrons enter degenerate orbitals. Well, I would like to use this word, whether we have it or not, singly. Well, the electrons enter degenerate orbitals singly first. That they enter single first. Whether I have a word singly or not, it doesn't matter, but the understanding is important. So, while writing, when do we actually apply Hund's rule practically? When do you encounter this Hund's rule is important. We encounter this Hund's rule while writing electronic configurations. While writing electronic configurations, then electrons enter degenerate orbitals singly first. Comma. Remember, he has not finished. Comma. He says, pairing occurs only when the degenerate orbitals are, and I would like to underline this, half filled. So I'm underlining few things. Pairing occurs, degenerate orbitals are half filled. That's what he says. Now he might say anything, but let's understand, we have our own understanding. We should have our own understanding. Right? Now, first of all, what is degenerate orbitals? What are degenerate orbitals? Now, if you actually see, if I say S subshell, 1s, you don't have further divisions in it. You will never see 1sx, 1sy, 1sz, and you don't have any further splits. S is S, that's all, right? No splits. No splits. So you can call 1s, 1 to be the first energy level, 1s to be again the same, you can say orbit, and S has no further divisions, so whether it is an orbit or orbital doesn't matter. Orbit or orbital doesn't matter. You must understand, because they don't have further what? Divisions, right? Similarly, if you actually see 2p, then you might have 2px, 2py, and 2pz, which you will write it like this. This is 2px, this is 2py, this is 2pz. 2px, 2py, and 2pz. You must understand, you have a split. That means P subshell, the 2p subshell is further what? Divided into 3 subshells, 2px, 2py, 2pz. And let me tell you, if you want to distribute electrons in this, you don't need to distinguish 2px from 2py and 2py from 2pz, except for the direction. But I think, and I wanted to tell you that the energy difference between 2px, 2py, and 2pz is same. You're just walking, that's all. In 2p cell, if you wanted to move, you just walk. You don't climb. You don't climb in 2p subshell, you must understand. You're not climbing. If you're climbing, there is energy difference. But since you're walking, the energy difference between 2px, 2py, 2pz is same, you must understand. So, orbitals of same energy, I draw the attention. Orbitals of same energy, where you wish to walk in them. You're not climbing. I'm not climbing from 2px to 2py. It's just a walk. It's just a walk, right? So understand that these orbitals have same energy level. All these 3 are having the same energy. Such orbitals are called degenerate orbitals. You must understand that. You must understand. So while writing electronic configurations, electrons enter degenerate orbitals singly first, and then after that pairing only occurs when the degenerate orbitals are half filled. Now let us understand why such a thing should happen, why electrons must enter singly, and why the electrons will pair after they fill the degenerate orbitals half filled. Let us see that why, technically why. You know, anyone can make statement and run away. But please understand that, let's understand this, because we have not asked this, teachers back in school, why, the electrons enter singly first and why they pair up once they are half filled, right? Also, what I will do is, there is a simple way of understanding practically what is Hund's rule of maximum multiplicity. And what is that? Let us understand this. So if I can rub this for you, I'm basically telling you his principle. Now we'll actually get into his heart. We'll get into his heart and know what exactly he wanted to tell us, right? Let us understand this. While writing electronic configurations, electrons enter degenerate orbitals. Now, this Hund's rule is only getting into your mind, and you remember him only while writing the electronic configurations. Electrons enter degenerate orbitals, that is orbitals of similar energy where you have splits. The D will have 5 splits, and then F will have 7 splits. So Hund's rule is only remember when the electron is entering into degenerate orbitals, not anywhere else. You just leave it off the Hund. Only remember while writing the electronic configurations, that too electrons entering what? Degenerate orbitals. They occupy singly first without pairing, and pairing occurs only when the degenerate orbitals are half filled. Now let us postmortem this, get into his heart, and answer a few questions which are there in your mind. I can read your mind, and I'm putting forward your questions on the board. Watch carefully here. Watch. Now, first of all, the first question which I wanted to ask, why electrons must enter singly first? Well, I don't know whether we have a word singly or not. I'm writing it for you. You must understand that, right? Don't worry about English, because there was an English guy who was born in England, later became the President of America, and then he was telling something about English, and he says that English is bastardization of languages. Now when I say that, it doesn't have a single origin. So don't worry whether it's a singly or it's a correct word or not. It's all about our understanding. I didn't say this statement. It is written in books. You can actually get through the books. And he is a Britisher. His mother tongue is English, right? So I just, if we understand, that's fine. The question is, why electrons enter singly? Why they must enter singly? Well, anything which is done for a purpose. Without purpose, you're not doing anything. You're not doing anything. If the electrons are entering singly, then there is something which is happening. Well, as far as science is concerned, if someone is asking why that's happening, why this is happening, why they're entering singly, why the reaction is fast, why the reaction is slow, for all the things in science, there is only one single answer. Only one single answer, mind you. There is only one single answer. One single answer. You don't look at, if someone is asking why the reaction is so fast, man, then you know to don't look at left or right. There is only one reason. And if someone is asking why the electrons are entering singly first, why not doubly? Then you have only one answer, and only one answer. And remember the answer, why electrons must enter singly first, the reason might to gain what? Stability. To gain stability. Now, what do you mean by stability? Everyone wanted stability. That's what we are doing every moment in our life. Similarly, it's no different from chemistry. In chemistry also, the atoms or the molecules, they break old bonds, they form new bonds. In atoms, within the atom, some rearrangement will be happening. Right? All this is done for stability. And if in sciences, what is stability? Is basically stability. I would like to write stability is a function of energy. It's basically a function of energy. And if you ask me correct relation between these two, then I can simply say the stability is inversely related to what? Energy. You must understand, lesser the energy, more is what? Stability. That's why you will see people with no energy will sit in that corner. People with more energy, like you teenagers in what? In intermediate, you will be jumping here and there because you have more energy, right? So stability is basically a function of what? Energy. So if Hunt is claiming electrons must enter singly first, right, there must be some reason. The reason is to gain stability. You must understand. Now, when you want to gain stability, stability is a function of what? Energy. And both are what? Inversely related. You must understand that. Inversely related. Lesser the energy, more is what? Stability. Now, if that is the case, why there is stability like this? I would like to illustrate here. Watch carefully. I wanted to write the configuration of nitrogen here. Nitrogen atomic number is 7. It is 7. Now what I'll do, I'll write the wrong way of Hunt and I'll write the right way of scheme of what Hunt given. If I can write the configuration to you, N is equal to 1s2, 2s2, 2p3, right? That is what is the configuration of what? Nitrogen. So if I can write it, it is 1s2, it is 2s2, because these two have, S has no splits. S has no splits. So the question of degeneracy doesn't occur in S because you don't have splits. And I come to 2p, then this 2p is divided into 3 compartments. Well, I would like to say 2px, 2py. This p orbital has direction. So I can simply say 2px, 2py, 2pz. This is the degenerate orbital. All the 3 compartments have similar energy. If you wanted to have a walk in it, you just walk it. You don't climb it. Right? I need to fill 3 electrons. So I'll fill it wrong way first. I'll go in for the wrong scheme. So I can fill it 1, 2, and 3. And that is wrong. And that will be given in the exam. Which of the following violates Hund's rule of maximum multiplicity? If he is saying that, of course, that is wrong. That is wrong. Because in the degenerate orbital, you should go singly first. So what is right here? What is right here is 1s2, 2s2, and then the 2p. I have 3 compartments, 2px, 2py, 2pz, and then we have to enter it singly. You have 3 electrons to fill. Fill it singly first. 1, 2, and 3, and when you enter, you must be with the same spin. Same spin. Don't write one here, again it's a violation of what? Of our principle. You enter the degenerate orbitals, you must be doing it in what? Same spin. That is one of the conditions for what? Hund's rule, you must understand. This is the right scheme of doing things. They enter singly first. Now the question is, why they should do this? Because that's what I'm writing. Why the electrons must enter singly first? The reason I told you they gain what? Stability. Stability is a function of what? Energy, and stability is inversely related to what? Energy, right? So why they should enter singly first? Let's understand this, right? So let me actually redraw this diagram for you. Watch carefully first. Watch. So the correct scheme, if I can write it, the correct scheme for entering into 2p, this is how is Hunt telling us. This is 2px, this is 2py, this is 2pz. You enter into this singly first. If this is 2p3, that is how you should enter. Now why you should enter? Listen to me here. Now remember that electron is a cloud. It's a cloud. It's not like a pepper seed or mustard seed which is shown in your textbooks. It is a cloud, and cloud has diffusing property. It will be diffusing. It's diffusing with an irregular boundary. You must understand that. It has a diffusing property. So if I can write this as a cloud, if I can redraw, mind you, if I can redraw, this is an electron cloud. This is electron cloud. You must dream electron to be like a cloud, not like a pepper seed with a regular boundary. No, a cloud doesn't have a regular boundary. You must understand that. And you have another cloud here. You have another cloud here. So this is the electron. This is the electron. I view it as a cloud. And the cloud has a diffusing property. When you are having a diffusing property, well, I understand that if my, when I live in an apartment, in a particular society, all the society members, all the society households have similar income to mine. I am a middle class fellow. So if I am living in a society, my neighbor also is middle class. So it becomes easy for me to venture into his house for asking sugar, salt, or any help. I can just straight away walk into him. But if you have a VIP next to me, it would be difficult for me because his way of life is different and I'm a middle class guy, so it won't be easy for you to venturing into a VIP's house. Similar to that, you must understand here, but here this energy level, and that energy level, all the three are same because this is nothing but a degenerate orbital. You must understand, when it's a degenerate orbital, the electrons' energies are same. They're same. So it's like as two middle class fellows living as neighbors, one will venture into the other. Similarly, what is happening is, since electron is a cloud, it has a diffusing property and it is free to diffuse to one over the other. So what it will do is this diffuses to this diffuses to this, that diffuses to that. And then when they're diffusing, each is merging with the other. And finally this degenerate orbital will somewhat look like this, and you have a bigger cloud. And I call this to be delocalized cloud. Delocalized cloud. That's almost like a similar to having a cloud over that. You must understand that. There is a cloud over that. Now what is happening during the delocalization, where the electron is moving from one orbital to the other, anything which you do results in loss of energy. It will result in the loss of energy. Just, you going to your neighbor's house and then playing with him, instead of playing in your house, you have only one bedroom. Now what you're doing is you're venturing into your neighbor, so you have total of 4 bedrooms and you're roaming around 4 bedrooms. That is called delocalization. Roaming in one bedroom, you lose less energy. Roaming in the entire 2 houses loses more energy. You must understand that. So the delocalization you lose what? Energy. When you lose energy, you gain stability. And that's why the electrons enter what? Singly. If you're not entering singly, then what happens? And singly with what? Same spin. These are the conditions for what? Delocalization. You must understand that. Otherwise, they don't delocalize. You must understand this. You can't expect, your people, the couples in your house, jumping around all the 4 bedrooms. You must understand, only single people without any pairing, right? They have the chance of getting into the others compartments, because you have same energy and form a larger cloud. When you form a larger cloud, the electrons, the energy is lost, and when it's lost, you gain stability. You must understand that, right? So that's why electrons enter singly. Now it's time to get into Hund's rule in a simplest way possible. Well, I'm writing a scheme. I think if you can answer that itself is Hund's rule. Watch carefully here. Watch. Suppose if I write this, watch carefully, I'm finishing it off. Now what is basically Hund's rule? What is Hund's rule? What is basically Hund's rule? Well, I write the configuration for you. Nitrogen, if I take 7, it is 1s2, 2s2, and here comes 2px, 2py, and 2pz. Well, I wanted to write what is Hund's rule. It is as simple as that. As simple. Watch carefully. Understand this. Here, we have 4 electrons. Right? This is 4 electrons. Now what I'm writing is you have to enter singly. You need to enter singly. So if this is 4, this is 5th. This is 6th. This is 7th. Of course, that we know, you can say. But remember, when pairing occurs, people go wrong. Watch carefully here. If the nitrogen, and then you have oxygen, 8. Then if I write 1s2, 2s2, and then 4 are finished, remaining 4 are left. So 1 singly first, and then go for pairing. Right? If that is the case, let's count it. Let's count it. I draw the attention of everyone. I draw the attention. Here lies the Hund's rule, the critical part of the Hund's rule. Watch carefully, I'm counting it. This is 4 here. This is 5. That is 5. And this is 6th. And this is 7th. And this one is the 8th. What people will do is the count in a very reckless way. How do you count it? You see, it is 4 here, then it's 5, 6, 7, 8. No, it's wrong. It's wrong. Then it's not Hund's rule. If you number it properly, it is Hund's rule. Now, what is Hund's rule? This is the 5th, this is the 6th, this is the 7th. It indicates that you have entered singly first. And the pairing occurs only after this is half filled. That means the 8th electron is this. Now if I can write the next one, fluorine, which is 9, then it is 1s2, 2s2, and then if I can write the degenerate orbital, then I think I'm writing the 5th electron, 6th electron, 7th electron, 8th electron, and the 9th electron. So if you count it in a wrong way, how do you count it? 4, 5, 6, 7, 8, 9. It's wrong. It's wrong. So let's count it. This is 5, this is 6, this is 7, this is 8, and this is 9. You must understand. If you count it in a wrong way, then I think you are going wrong in Hund's rule. Finally, let us write neon. If you write neon, it's 10, then it is 1s2, 2s2, and here is the p orbital, and then 5, 6, 7, 8, 9, and 10. So this is 5, this is 6, this is 7, this is 8, this is 9, and this is 10. You must understand, if you are able to count it properly, then you are actually through and understood what Hund's rule. You must understand this, right? So why people enter singly? That's because when you enter singly in a degenerate orbital, first of all, understand electron is a cloud, and the cloud won't sit quite as you and me. It has a diffusing property. It tries to diffuse from one orbital to the other. When you actually diffuse, then there is delocalization, and there is delocalization, then you have a larger cloud. You're now moving in a larger area. You lose energy. So then you gain what? A stability, partial stability, you must understand, within the atom, right? Further stability you get it when you actually go in for bonding. So anything is done for a purpose. Without that, you're not doing it. So Hund has actually observed it. He has observed it. So simply speaking, if you wanted to explain Hund's rule to someone, how do you do it? How do you do it? Well, forget about all this. Forget about all this. How do you explain Hans rule? Well, I'm actually concluding this by writing this configuration of neon. So if I can explain to people what is Hans rule, so if I can write the configuration 1:2, 2:2, and then if I can fill this, right, if I can fill this, and well, if someone is counting like this is 4, this is 5, this is 6, this is 7, this is 8, this is 9, and this is 10, then this is wrong. It's wrong. He doesn't know Hans rule. What is right? It is right. So if you can write this 1:2, 2:2, then if you have singly first, then pairing occurred, and the naming is important. Till here you have 4. This is the 5th. This is the 6th. This is the 7th. This is the 8th. This is the 9th, and that is the 10th. If you are naming it properly, then you must understand that you understood Hans rule. Right? Thank you. My appeal to all of you is follow me, follow Tone Academy, follow T1 channel, bank on us, because we will be following the sequence, and every subtopic I'll be linking this to the JEE or the pre-engineering test. So just relax at any point of time, just to click on the T1 channel, Tone Academy, subscribe, and I'll be there. Along with me, we host the best faculty available for you. Thank you, and thanks for listening.